How many are there? Right. Okay. YouTube में? Yeah. Okay. I'm very happy to introduce Dr. Somayazulu, who has graduated from the 25th batch of BRC Training School and joined Neutron Physics Division. And in Neutron Physics Division, he pursued both theoretical and experimental high-pressure research. And in 1991, he obtained his PhD under the guidance of Dr. R. Chidambaram. And subsequently, he went on postdoctoral fellowship to Geophysical Laboratory of Carnegie Institution of Washington in 1994. In Carnegie, he was into research on materials under extreme conditions. In 2019, Dr. Somayazulu moved to Argonne National Lab into this X-ray science division, and where he joined HPCAT as a group leader responsible for high pressure research with 4 dedicated synchrotron beam lines at the advanced Photon source in Chicago. Dr. Somayazulu's research interests lie at the crossroads of materials physics and high pressure and high temperature chemistry. He uses a variety of experimental techniques to explore the change in bonding and formation of novel materials. He has many collaborations with groups performing simulations to understand various phases of matter which are formed during these extreme conditions, and also predict novel material properties. Dr. Somayazulu has made important contributions to the physics of complex hydrides, leading to the realization of molecular metallic hydrogen. He has several important discoveries to his credit, such as formation of CH4, H2,4. It is not just a chemical kind of a thing, CH4 and H2 4 times. And xenon hydride, similar, H2,8. The icing on the cake is the discovery of superconductivity in lanthanum hydride. I think it was at a temperature of about 260 Kelvin under pressure, which is just below the room temperature. He has been a part of the team that has consistently advanced synchrotron X-ray diffraction using diamond anvil cells, and has worked on several cutting-edge developments that include laser heating, pump probe measurements, and single crystal diffraction at megabar pressures. I invite Dr. Somayazulu to deliver his talk, The Quest for Room Temperature Superconductivity.
Thank you, Ravi. Thank you, Professor Vasudevan. It's a pleasure to be among old peers and colleagues. Takes me back many years. Ravi was in fact my junior in the university, so I know him from a long, long time ago. And I want to make one comment about today's talk. You know, when I started preparing for this talk, or when I was invited, Professor Vasudevan wanted me to make it a talk which would be amenable to a larger audience of people who are interested in understanding the merge, or the marriage, should I say, of room temperature superconductivity and high pressure physics. And so I will try to do it to my best of abilities. I am, of course, also honored to have my earliest physics teacher, Professor Bhatnagar, a part of the audience. So I feel really happy about it. So what is the meaning of trying to have room temperature superconductivity, and why does high pressure physics come into it? Let's go into that. This is the plan of my presentation. Let's look into what pressure-induced chemistry does. You know, I mean, it's something which people, I think, miss, but it's really the window into new materials. All of you who have diamond rings will understand that that diamond was created under pressure and temperature, and it's one of the most wondrous materials nature has ever created for us. And that is what pressure can do in a way. Metallic hydrogen, you know, I mean, why is it such a big deal for high pressure physicists? I mean, every advancement in high pressure experimental techniques has been driven by metallic hydrogen. So in a way, you know, people always ask, what's the big deal about metallic hydrogen? I will try to talk a little bit about that. Metal hydrides and molecular hydrogen complexes are something which came out of this kind of study of quest for metallic hydrogen, and in a way have enriched our understanding of material science and metallurgy of materials in a big way. And especially in today's technology, when you want to understand how to make hydrogen efficient economy, I think molecular hydrogen complexes form a very big role in that. And then, of course, the race to higher transition temperatures has been a very close interplay between theory and experiment. I think it's amazing. There has never been such a good interplay between theory and experiment. And in a way, that is what has driven this field. Although to an extent that there are a lot of people sitting out there and thinking that one is cheating the other in terms of predicting higher TCs and finding higher TCs. Now, lanthanum hydride itself, something which I will talk about, but not too much in detail, is a rather quixotic result in terms of how the transition temperatures are varying, or how we see higher and higher transition temperatures. And it keeps telling us, are we missing something? Are we trying to find something which is very simple in a binary system and actually missing something? And that's probably what the latest discovery from Ranga and co-workers has shown in the system of carbon, sulfur, and hydrogen. Not only that, of course, it has raised a number of questions. Is BCS or not BCS the holy grail, or the holy description of superconductivity? And do we actually care whether it is BCS or not BCS? And of course, finally, we'll try to do a little bit of discussion about how we can transition from discovery to maturity, because after all, at the end of the day, we have to be relevant to the taxpayer who's paying us money to break so many diamonds. Okay. So pressure as a thermodynamic variable. I mean, we all go back to our grad school kind of physics, and we say that, okay, Gibbs free energy is basically a volume term and a temperature term. Okay, the volume term is the work you do in work you have to do to attain a certain volume V, and the entropy term is linked with temperature, and it's the heat you use or give up for a system to equilibrate with the environment. So very simply, what you have here is what you have here is the curves for various possibilities of combinations of PV and TS. And of course, we are all taught to understand that when your system is able to overcome the hump given by this delta G here, it goes into a state in which is stable, which means that you're able to overcome the reaction barrier and proceed forward. Now, so this is what we understand, but this is also central to understanding what happens, because pressure as a variable and temperature as a variable are two driving forces to chemical reactions and to make new materials for us. Typical thermal expansivity of a solid, is about 10 power minus 5 per degree centigrade. And the typical isothermal compressibility of a material is about 10 power minus 9 per Pascal. Now, but what does it mean? Let's look at it in a bigger context of the universe. So if you look at the range of temperatures in the universe, you see it ranges between about, close to absolute zero, about 10 power minus 9, 1 nanokelvin, let's say, to inside the hot stars, which is about 10 power 9. So essentially, you're seeing an order of magnitude range of temperatures. And I've put some milestones of the temperatures on the left here, which go from, which span about 10 power 18 or 18 orders of magnitude. That's pretty much the range of temperatures available in the universe as we understand it, okay? On the other hand, let's ask the question, what are the range of pressures in the universe? So if you ask the question of what are the range of pressures in the universe, it's much larger. It's almost about 10 power 25. So it's a huge range of orders of magnitude change in pressure that can affect materials in the universe, or tell us how the universe has propagated or formed. So one of the great things is, I mean, if you look at what we can achieve in a lab, for example, you can go from 10 power minus 14 or 10 power minus 10 to about 10 to 10 power 16 at NIF. So there's a huge range of achievable conditions in the lab which allow us to access this. So it's one thing to know that these exist within the universe. It's another thing to know that these exist. These can be actually held in a lab or looked at a lab. Now let's ask the question, what actually happens when you go across these pressures? There's a very nice article which I would urge people to look at, written by Grosella and Rolf Hoffman, who actually look at what chemistry what happens to chemistry at high pressures. And it's pretty intriguing because of the fact that a lot of these are something we have been discovering in the lab, and they have actually triggered theoretical calculations. So, quite tongue-in-cheek wise, they tell you that the smallest pressure you can get is when you go dancing with a lady with stilettos, and who can set, and all the way up to what happens in an economy in terms of pressures of monetary balances. But notwithstanding that, what we understand is in the lab, we can generate pressures. But how do we generate these pressures? In fact, in the lab, you can generate pressures and temperatures, which makes it a very interesting interplay. The simplest device which people have is the diamond anvil cell. There are a variety of diamond anvil cells, and there are all kinds of probes which you use with the diamond anvil cell. But the most common probe which you use in the lab is the synchrotron. Most common probe which people use is the lab-based Raman systems and the synchrotron-based microprobing systems. And the idea is that you can achieve pressures of the order of about a terapascal or 100 GPa. I will come into what I mean by terapascal and 100 GPa shortly. But essentially, what you do is you take a material which you want to study and squeeze it between two diamond anvils and probe it with a laser beam to be able to achieve the pressure temperature conditions. And of course, as all of us know from our high school, pressure goes as force per unit area. So higher the pressure you want to go, smaller is the area. Smaller is the area implies that smaller is the microprobing technology you need, and that is where synchrotron beams come into play. Okay, but that's in static pressures. What about dynamic pressures? There are various ways of doing dynamic pressures. It turns out that in dynamic pressures, your range of pressures and temperatures are much larger. And of course, consequently, the time at which you achieve these are also smaller. But I just wanted to give you a flavor of that. There are almost laboratory-based laboratory-based techniques like the gas gun, and you can go all the way up to the NIF, where you can go up to hundreds of TPA, which is going to it's about 100 times what you can get from a diamond anvil cell, and about 10 power 5 Kelvin, which is about 100 times again the kind of temperatures you can get in a diamond anvil cell. So you have, of course, there are more nuanced things like the strain rates which are involved and the times over which the pressure is applied. We'll not get into that, but the idea is that you can, in a lab, you are able, or in a synchrotron beamline, you are able to achieve these kind of conditions and study materials. And that is what makes it interesting to be able to do high pressure physics or high pressure chemistry. Now, what does pressure do? As I told you, I'll give you a little bit of an idea about what pressure and energy is correlated. So typically, if you look at 160 GPa, which is about 1.6 megabars, if you do the conversion in the table from the top, I told you, and 1 atmosphere is 1 bar, 160 GPa is 1.6 times million atmospheres. That corresponds to about 1 EV per angstrom cube. So already you're beginning to see what pressure does. Pressure begins to put an enormous amount of energy into your system. And in fact, if you talk about 1 EV per angstrom cube, you're beginning to talk about situations where you are pushing two atoms closer than what they would be in the closest approach in a van der Waals curve. So already you're beginning to tune the bonding between elements. And so that is signified here. So in other words, you can say that pressure changes the periodic table. I mean, that's what this cartoon here says, that pressure completely modifies the periodic table. So for example, here, since the theme of this talk is superconductivity, let's look at elements. You see that at ambient pressure, all those elements are listed in red are having a superconducting transition at atmospheric pressure at various temperatures. The minute you start applying pressure, you literally double the number of elements which have which show superconductivity. In fact, the highest temperature of superconducting materials is in sulfur, which is at a fairly high pressure. So what it tells you is that pressure tunes the bonding and therefore the electronic properties of materials, and therefore makes new possibilities. But then you also have this situation. I mean, I just picked up this from some available review, where you can change the state of the bands in a material. So for example, you can increase the overlap between the conduction band and the valence band in materials, and you come into the very often known phenomena as pressure-induced metallization, and which is pictorically shown here, that something which is optically transparent is becoming optically opaque or metallic. And at the same time, releasing the pressure brings it back into its insulating or non-metallic state. And quite simply, what it means is that as you increase the pressure, there is overlap between the bands, and in effect, which is shown here in this cartoon or in this diagram on the right here, in effect, what you do is you bring a metallization just because of band, the overlap of the metallic and the conducting and the valence bands. Of course, there are again nuances here. Is it a direct band gap or an indirect band gap? We'll not go into that. But in a rough way for a general audience, you can understand this if you picturize it with respect to your simplest solid-state physics background. Now, on the other hand, what I wanted to talk about is the interesting part, the counterexample, that something which is metallic can become insulating. So it is almost counterintuitive into thinking as to what happens. And this is a brilliant paper which came out in 2009, which talked about how sodium becomes transparent at increasing pressures. And in fact, you can see it from the pictures here that you look at sodium at lower pressures, it is metallic and it is reflecting. And as you go to higher and higher pressures, especially at about 150 GPa, it becomes black, and above 200 GPa or 180 GPa, it becomes transparent. So in effect, this is almost counter to what I was talking earlier, but it tells you that something more interesting is happening when you bring atoms together, or when you bring when you increase the pressure on materials. In this case, you form what are called interstitial quasi-particles or electrides. So this is again a great. It's almost a paradigm-changing kind of an understanding of physics in terms of the fact that in a very simple way, the repulsion effects take over, and one can think of it as an idea, as a problem where the Coulomb repulsion and the Pauli exclusion literally drags the electrons from between the atoms into the interstitial sites and creates what is known as an electride. And this, to a certain extent, again, is something which is counterintuitive, but again, something which pressure can do. And that itself is a very interesting phenomena in materials. Why am I talking about this? Is because it has its bearing in some of the other things we're going to be talking about shortly. Now, let's look at what metallic hydrogen. Hydrogen is the dominant element in the universe, of course, and we want to understand what pressure does to hydrogen, because in a way it explains how the universe was formed. But more interestingly, it is a link to our simplest problem in quantum mechanics, which we can solve exactly. So in all things considered, it's the simplest problem you want to understand. You take, if you go on squeezing on hydrogen, what is going to happen if you apply pressure? And in 1935, there was this intriguing paper which came out by Wigner and Huntington, who predicted that the hydrogen would become metallic with increasing pressure. Of course, the pressures at that time were marginal. I mean, people were not able to apply very high pressures, and what they thought was a very high pressure was something which was about 30, 40 GPa, at which they predicted it would become metallic. And consequently began the journey, or the quest for looking at metallic hydrogen, which essentially drove high pressure physics to a lot of extent. Now, I can jump from 1950 or 1960 to all the way to 2000, and we are literally looking at very huge advances in experimental technologies in terms of high pressure physics to ask the question as to what has happened to hydrogen. There have been 3 papers in 2011 by Ermetz and Troyan in Nature Materials, where they talked about conducting dense hydrogen. There is a paper from Ranga and Ike Silvera, where they actually said, it was published in Science, where they claimed that they had observed the Wigner-Hunting transition in metals, in hydrogen. And there is a more recent paper from Lubert and Ocelli, where they have synchrotron evidence. But the sum total of all this is over many developments of technologies and many changes in experimental approaches, there seems to be a nebulous detection of metallic hydrogen at pressures of the order of, I would say, right now we are looking at about 450 GPa when hydrogen becomes metallic. Now, is this the end of the story? No, because obviously we still need to understand what Ashcroft meant in his paper. I'll come to that later. But the success in shock has been different. They have been able to make metallic hydrogen and deuterium under shock compression. And this has been possible because of the fact that they have been able to make liquid metallic hydrogen and liquid metallic deuterium due to the high pressures and temperatures that they were able to achieve. And these are 2 great papers which came out on this, which is Sam Weir's paper in 1996 and the paper by the Sandia group and in 2018 on deuterium. Okay, so much of an aside on what is happening there. But what we are trying to understand is the fact that way back in '68, Ashcroft had predicted that metallic hydrogen would be also a superconductor. So the intriguing thing was that can we make metallic hydrogen, which is also a room temperature superconductor? Of course, as I told you, the journey was very difficult because there were a lot of situations where people were not able to achieve the kind of pressures and more importantly, not able to measure them. In fact, those 3 papers which I talked about have different ways of looking at metallization in hydrogen, and all of them are not conclusive. So one of the proposals put out by Ashcroft was that, wait a minute, I mean, why are we looking at hydrogen? Why don't we look at hydrogen dominant metallic alloys, for example? Or can we change the transition, insulator metal transition in hydrogen by somehow doping the hydrogen band gap itself with impurity states, which will close the band gap at lower pressures? Now, these are intriguing possibilities, and that is what started this campaign in trying to make alternate ways to reach metallic hydrogen. Okay, so, and Ravi in his introduction was talking about the CH system, and one of the earliest thinkings was that, the carbon hydrogen system is an excellent system to consider. Again, it was discussions with Neil and others that drove us to look at it. But what happened was actually, so this was the beginning of this kind of work where people were looking at hydrogen complexing with other materials to be able to form high pressure compounds, which can in principle replicate metallic hydrogen. Okay, so what was understood was that actually, the van der Waals forces stabilize a number of compounds. So this was something different from what was existing in common understanding about where how materials are formed or how molecular compounds are formed at high pressure. The fact was that the level of understanding at that time was that when you take molecules and compress them in a diamond anvil cell, essentially the forces which bring them together are like Hart spheres, and you form non-interacting spheres which pack well, and the entropic contribution drives the formation of materials. I think the complex phase diagram which we found in methane and hydrogen for the first time opened up the possibility that van der Waals forces are not as simple as that, and that they stabilize a number of compounds based on the kind of forces you tailor. And not only that, I think the other important thing which came out is that many of these compounds could be quenched to ambient pressure, albeit at low temperatures. And one of the amazing things which came out of this study was the fact that you could make a compound with a hydrogen concentration much higher than what would ambient pressure or ambient temperature kind of calculations tell you. So obviously, of course, I'm going through about 25 years of work in trying to explain the fact that there have been very recent calculations where they actually put together, which is a 2019 calculation, where they actually put together, the van der Waals forces, take into consideration the van der Waals forces and do a quantum mechanical first principles kind of calculation and predict the formation of various compounds and show the enthalpy curves do actually match with the experiment. So what I'm trying to tell you is that on one hand, while people were looking at simple hydrogen, whether it was under dynamic compression or static compression, there was a concentrated effort, but it was blind in trying to understand what kind of molecular systems we can look at to efficiently dope hydrogen to be able to manipulate the metallization pressure and to be able to make metallic hydrogen or metal dominant hydrogen materials at lower pressures. So that was where this was. Now, again, it turned, we went back to chemists, and chemists at that point of time pointed out that the problem with trying to dope hydrogen with carbon, or in fact, at that time, there was a study even on doping hydrogen with H2O. The problem with doping hydrogen with some of these materials is that they're electronically benign. In other words, they are not contributing in any way to the formation of higher hydrogen complexes, which is what you would want to be able to bring hydrogen molecules at a closer distance. So that was when we started looking at xenon and hydrogen. And this was, again, full of surprises to us. First of all, we found that you can form a huge number of phases. And I'll just try to lead you through this pictographs here. So if you take this is when you're looking through a diamond anvil cell, this is what you would see if you take a mixture of xenon and hydrogen, which would be just a homogeneous mixture because it's completely miscible. At about 4 GPa, you see the formation of a crystal. And at about 4.5 GPa, we found that there was a phase separation and formation of two different kind of phases. And with increasing pressure, you get different kind of compounds and different kind of compositions. I will not go into the gory details of all that, but this was one of the first measurements where we actually did single crystal diffraction, and we were able to achieve things like, get the electron density of this van der Waals compound and study the electron density as a function of pressure. And that was a big leap forward in terms of the ability to understand what is going on. And I think the most important part is that you could form an extraordinarily high hydrogen concentration in this material. In other words, you're forming a material in which you have up to 8 hydrogen molecules latched onto a single xenon. For people in the xenon community, it was not a surprise. I mean, if you take xenon chlorides, in fact, there was a Nobel Prize awarded for that, called the Bartlett compounds, that as you increase the pressure, it is possible to form higher oxidation states of xenon and therefore latch on higher number of hydrogen molecules per se. But what is the intriguing part of it? The intriguing part of it is that, firstly, as you increase the pressure, the hydrogen-hydrogen vibron frequency fell down, as and that seemed to imply that xenon is beginning to tune the hydrogen-hydrogen interactions, which is what we want, because that is the driving force of trying to make molecular metallic hydrogen. And but on the other hand, what we found is that there is an unexpected stability. The highest pressure we went up to was about 260 GPa, 2.6 megabars. And what you find is there is nothing in the infrared which is even suggesting remotely of any metallization in this material. And not only that, what is more intriguing to us was that if you calculate the xenon-xenon distance, and if you based on the volumes which we observe, xenon-xenon distance shows dimerization. Not only that, xenon itself metallizes around 150 GPa, but that distance is achieved at fairly low pressures. But in other words, the metallization of xenon sublattice within this compound does not do anything. Now, that is a big surprise to us, but in terms of that sodium experiment which I put up earlier, or the sodium result which I put up earlier, it tells you that life is not so simple. So in other words, you can have a material like xenon, which is highly electron donating in the hydrogen sublattice, and it will do nothing to the hydrogen metallization or change the pressure in hydrogen metallization. Obviously, because what is happening is as you increase the pressure, the electron density seems to be spilling into the interstitial regions. So this, I mean, I think in a way it was linked to that. But what I would like to point out is this started calculations from the theoretical community, in particular the Cambridge group, who wanted to understand, firstly, what is the reason for the stability of this kind of a compound? Secondly, why is it that even at such high pressures, this compound is not metallizing? Okay. And I will skip through a number of their results. I'm not going to that. But I think it was at that time there was a reassessment of where these molecular hydrides are going. And, this is, I'm picking up a slide which was presented by Neil Ashcroft, in fact, in one of our meetings we had, where, he pointed out that, look, what you want is high phonon frequencies, right? So obviously it means that, okay, from a BCS perspective, I'm assuming all of us are fairly familiar with the BCS theory. From a BCS perspective, what you want is you want high phonon frequencies and you want large electron phonon coupling. Quite simply, if we just stare at the periodic table, it means that you want to combine elements here, like hydrogen, lithium, beryllium, sodium, magnesium, with elements in this side of the periodic table, like boron, carbon, nitrogen, oxygen, and so on. So, in other words, you want to have combination of these elements, but you also want to have a large density of states at the permeable surface. So, I mean, it's a very simple way of saying that you want to do these things to be able to get these superconductivity in these materials, which can be formed with hydrogen-rich compounds, and pressure will hold the key. So this is the kind of idea it was prevalent at that point of time, and so I think the question then one asks is, okay, if I tell you that this is what is the underlying philosophy, how is it that we're going to get there, right? So all of us in this business of material science know that synthesizing new materials is very difficult. I mean, if somebody throws the periodic table at me and then says, okay, take your pick and start doing experiments, it's going to be a lifetime. There are a huge number of possibilities, and the problem is that most materials which are available to us off the shelf in our chemistry lab are materials which have been created at ambient pressure. So obviously they don't mimic some of these properties we want, or they don't help us make these new materials. So where do we want them? Why do we want them? Mankind is having a lot of trouble. We want new energy materials. We need wide gap solar materials. I mean, I'll give you an example of why this is important or how this is going. In the PRL this week, you will see a paper on silicon-6, hexagonal silicon, which has a different band gap as compared to other silicons, and this other known silicon allotropes. And this silicon was synthesized at high pressures and temperatures at HPCAT. Again, due to an allotrope of silicon, which is silicon-24, which is again synthesized at high pressures and temperatures. So now you're beginning to see that there is a focused idea about how to synthesize new band gap materials, new battery materials, new fuel cells from using pressure, but using directed synthesis. Harder than diamond, you want structural materials which are higher in rigidity, higher strength, lower corrosion resistance. You want higher TC, you want more energetic materials. All this is possible with materials by design. And what does materials by design say? So let's take a small detour and ask the question, how do we, can we predict how materials are formed? Or, the problem is, as John Maddox put it in this Nature Views in '88, it is impossible to predict the structure of a simple crystalline solid. And I mean, that's what keeps all the crystallographers at work. But with all these advances in computational physics and computations and chemistry, we are still not able to do this properly. But it turns out that there has been a race for it, and there have been several groups which have made great progress. I can name some of the people like Arten and Eva and Yanming Ma from China, who have succeeded in building a big school of people who can use these evolutionary algorithms for predicting crystal structures. Now, although at this point of time, these are algorithms which take any two elements on the periodic table and crunch them through a huge series of simulations to be able to predict the energy, the enthalpy curves, and tell you what are the stable compounds that you can form, and predict even the properties of those compounds. It tells you that you have now come to a situation where you don't have to kind of go into the lab and throw a dart at a periodic table anymore, but you have theoretical computational people tell you what you need to look at. And that is where the story of this high temperature, room temperature superconductivity goes. Okay, what do I mean by that? Let's look at this. There is this prediction by Ashcroft that you need hydrogen-dominant metallic alloys, and they could form high-temperature superconductors, right? Now, it turns out that when we looked at carbon and hydrogen system, we found a system in which, for some reasons, the van der Waals forces stabilized, but at high pressures, the system behaved in a way which did not implicate that it would be a hydrogen-dominant metallic alloy. I'll not go into the details of it, but it turns out that we could think of substituting carbon in that with hydrogen, right? With sulfur. So again, it is going back to that periodic table I showed you. And you could now, instead of looking at methane and hydrogen, you look at hydrogen sulfide and hydrogen. In fact, that was the first experiment we did way back in 2010 when we looked at hydrogen sulfide and hydrogen, because we wanted to understand how this structure, which is hydrogen sulfide and hydrogen, would mimic methane and hydrogen behavior, but with tunability in the electronic or the intermolecular forces. And what we did find is that there are new kind of interactions and there is new kind of structural ordering. That was the driving key, that the new kind of interactions which you could get under pressure gave rise to new structural ordering. What it did was that it generated this theory group to start looking at pressure-induced metallization of dense hydrogen sulfide hydride. And they predicted that actually it would be a high-temperature superconductor. So the next in the series of things was the fact that actually there was a paper which came out immediately when looking at hydrogen sulfide, which showed that at high pressures, you could get a transition temperature of the order of 203 Kelvin in hydrogen sulfide itself. Although at that time, people were under the assumption that it was H2S, we now know, because of the consequent calculations by Ion Area and others, that it's actually H3S, which is a strongly enharmonic phonon-mediated superconductor. So you see the way the interplay has been between experiment and theory in very, very rapid succession within years of each other, due to the maturity in both the experimental and theoretical techniques. And of course, there was then the prediction that you could have a route to higher TC with methane intercalated hydrogen sulfide hydride perovskites. And this was, again, a calculation which came out at that point of time from geophysical lab. And you had the culmination in room temperature superconductivity in carbonaceous sulfur hydride. I'm not going into details in a number of these things, but due to the fact that there are a huge number of experimental and theoretical complexities involved, if people are interested, we can discuss this towards the end, but because there is a certain aspect to this. Okay, so this is one route, right? I mean, we said we can form these molecular compounds with hydrogen, and these molecular compounds with increasing pressure are going to give rise to different structural candidates, which are possibly going to have high temperature superconductivity. But what about the metallic hydrides? I mean, what if you took actually existing metallic hydrides and squeeze them and increase pressure on them? Would they metallize? In fact, this is a very interesting paper which came out in 2010, which is again Marco Polis and Roald Hoffman. I must point out that Roald Hoffman is a Nobel laureate and is a very brilliant chemist who understood this problem of where metallization occurs in hydrides and hydrogen dominant materials, and was suggesting that we look at something like the highest hydrogen content materials, and one of those was the barium rhenium hydride. There is a whole class of materials, I will not go into that, which is barium rhenium hydride, sodium rhenium hydride, lithium rhenium hydride, and so on, which again are telling you with respect to that simple-minded periodic table I showed you, that you have these light elements like sodium, lithium in them, and the hydrogen, and the intermediate being a rhenium. And so after some amount of work, we realized how to synthesize these materials and load them in diamond cells and do these transport measurements at increasing pressures. In fact, I remember that this was in the early days when I actually gave a physics colloquium in BARC and I was talking about this. But you realize that with increasing pressure, there is nebulous signatures of superconductivity, but not so superconducting. I mean, as you can see, the truthful curves presented here seem to indicate that you do get a transition where the resistance is dropping, but things don't seem to be very good. Now, this intrigued us. I mean, there was nothing structurally we could find which said that it is not wrong. I mean, with respect to where the theory goes and where the experiment goes, we are converging, but we are not quite there yet. And so the question we asked is, what is happening in these materials? And what is the reason that this is not happening here? And then we realized that we don't see a dissociation. I mean, the obvious thing to ask was, I must say that I missed something in not telling you that in the case of hydrogen sulfide hydride, there is a bunch of experiments which we now know which showed that there was dissociation. So, just as sodium behaved as an insulator under extreme pressures, you can have situations where you make the material and as you keep increasing pressure, it dissociates. So there is no dissociation in this. How do we know that there is no dissociation? Of course, all of you out there who are expert crystallographers will say, have you seen hydrogen? No, we don't see hydrogen. We only look at volumes, and from that we deduce how much hydrogen is there, which is a very indirect way of looking at it. But we can also do Raman spectroscopy, and that is something which I will not talk about here. But what was surprising to us, it's a really interesting result, is that while there is no dissociation, the disorder in the rhenium-hydrogen bonds under pressure seems to cause it to form a poor semi-metal. How do we know? If we look at reflectivity, and you can do the analysis of the reflectivity in these materials, what is traditionally known as the tau plots, you see two kinds of linear regimes. It's almost as if that the material is a poor semi-metal. Now, what does it mean? It means that as you increase the pressure, your hydrogen content may not change, but because hydrogen is such a light element, and more probably because 0-point motion becomes important, the hydrogen-hydrogen interaction gets tuned in such a way that you start forming a kind of a poor metal. Now, the beauty is, I mean, what it tells you is that there is a certain amount of hydrogen disorder under pressure which will affect your transition temperatures. And I think we are coming to that situation today in that we are beginning to understand that this is parallel in the hydride superconductors, also causing a considerable amount of confusion among theorists as to what is the cause of superconductivity in these materials. Okay, now, obviously, I'm skipping through a number of years of very intense research, but what finally came was, people said, okay, what are the theoretical signposts for hydride superconductors? It's not just, combining elements on two sides of the periodic table. There is something more than that because of the fact that you want something which is going to be stable. You want a material which is going to have the right combination of elements. You want the material to have the right combination of structures and the structural characterization, which will give rise to this hydride superconductivity. And What it turned out is that this is something which I'm picking up from this excellent physics reports paper, where they look at this existing understanding from theory and experiment, and kind of draw a conclusion as to where things are going with respect to transition temperatures and the combination of elements in the periodic table. What they do find is that at very low pressures, for example, we all know palladium hydride exists. What is the motive for that? You just have one hydrogen per palladium, okay? And the transition temperature in this is as low as 10 or 11 Kelvin, although there have been very recent reports of high transition temperature in palladium hydride of the order of about 30 Kelvin. It's a controversial paper, but I think, again, pressure, some of our recent results or some of our recent work on palladium hydride under pressure has shown that there is a possibility that you could increase the hydrogen concentration. I will not go into that at this point, but look at the conventional knowledge we have of palladium hydride, which is existing at ambient pressure, which has a very simple cubic structure where you have one hydrogen. You go to about 120 GPa, you have phosphorus hydride, which has two hydrogens per phosphorus in a arrangement which is having a higher transition temperature, but still you only have very small amount of hydrogens per metal. On the other hand, sulfur hydride H3S, which superconducts at a whopping 203 Kelvin at 160 GPa, has this combination of hydrogens, a clathrate-like cage of hydrogens surrounding sulfur. And obviously, this is the structural motif, which is possibly contributing to higher transition temperature. Go to lanthanum hydride, which we worked on and showed that the transition temperature is as high as 265 Kelvin. You find the structural motif has changed. You have a larger number of hydrogens sitting around the lanthanum. So as you see, look at the progression of structural motifs, which I'm pointing out here, you can understand the fact that the metal is constituting, is holding together the hydrogens in a particular way, which is allowing a structural motif to exist, a clathrate-like cage of hydrogens to come together, which begin to mimic which begin to metallize and form the superconducting hydride configuration. And of course, at the end, I put what would be the metallic hydrogen at about 400 or 500 GPa, again, based on theoretical simulations. I mean, there has been no structural study so far, where you can see the configuration of hydrogens. So obviously, from a very structural concept, you can understand that this is what is driving the higher and higher transition temperatures, the ability or the propensity to form these clathrate-like structures with the hydrogens in there. Now, so what do we know? We know that the superhydrides, which have high transition temperatures, I've not gone into a lot of details here, but have a clathrate-like framework, okay? And that clathrate-like framework, in fact, starts to mimic metallic molecular hydrogen. Now, I have a plot here, which I'm sure you will all see, where, we have kind of plotted where the transition temperatures have gone since the discovery of hydrogen. In fact, silane was one of the first hydrogen-dominant materials, which was shown to have a high transition temperature, superconducting transition temperature. And you will see this huge, jump in transition temperatures as with increasing in a plot of transition temperatures versus pressure. So phenomenally high TC. Now, the question, of course, all the people who are superconductivity experts and people who are thinking in terms of BCS and non-BCS would ask is this BCS or not? What is your typical currents? What is your typical JC and HC and kind of things? Unfortunately, there are two problems here. One is the fact that the simplest thing we can do is transport measurements. The size of sample is so small, it's very, very difficult to consider other measurements, especially under magnetic fields. Towards the end of the talk, I will talk about some of the measurements which have been done in the Maglabs, which have been done in Dresden and other places, where people are, and Los Alamos, where people are beginning to use higher and higher fields to be able to understand this problem in terms of what is the way the critical field, what is the measure of the critical field in these materials, and where is the systematics of this critical field going. And of course, structure predictions are great. Materials are by design, but they are looking at binary systems. Now, is it possible that we are missing the whole forest by looking at this tree of the binary binary hydrides? Okay, I just want to take a deviation, a small detour into where experiments are going in terms of this thing. So here is an experiment. I'm just presenting some of the details from our unpublished data based on, in a certain way. I mean, I think it also corroborates with some of the published data which has come out in recent days on the system. We looked at sulfur and hydrogen, which was simple because hydrogen sulfide is something you can load into a diamond cell, and people looked at it. Now, what about selenium and hydrogen? Or what about a solid solution of sulfur and selenium in hydrogen? Is it possible to do this? And how does it tune the transition temperature? Why? Well, the question we're trying to address from this is, how does the central metal atom contribute towards the transition temperature? And what is its contribution in this whole system? Okay, so it turns out that you can actually dope sulfur and selenium. You can mix sulfur and selenium and modify the stoichiometry, and it's a very continuous curve. You can change sulfur and selenium as much as you like, and you can form a solid solution. And from the Raman spectroscopy, we know that the selenium is going to the same site as sulfur, and it's tuning the interactions appropriately. You can actually see a sulfur hydrogen, selenium hydrogen kind of vibration, and the tune and the effect it would have on the hydrogen vibron. Again, a lot of detail I'm not going into, but just kind of giving you an idea. This is a typical way we measure. What you see here, this bright circle is the QLET at the diamond angle. That's about 100 microns here. And the sample size, which is in this case a selenium hydrogen sample. In fact, this was work done by one of your colleagues, Ajay Mishra from PARC, is encased between 4 electrodes on which we can do van der Pol measurements and electrical conductivity measurements in a cryostat. And this sample size is of the order of about 30-40 microns. We can get great diffraction from HPCAT on a synchrotron beamline and actually evaluate what the structure is looking like. And so we know, for example, we can do a refinement of the occupancy of sulfur and selenium. We can also do Zane's measurements. I'll go into that more in detail later. But what it shows here quite simply is that as you replace sulfur with selenium, your transition temperatures drop. And the drop in transition temperatures follows the systematics, which can be used by the theoretical people to actually understand what the modulation of selenium, sulfur or selenium is with the whole hydrogen clathrate cage and how it stabilizes it. So in other words, it's not, and it's all based, of course, on transport measurements. And this is an example of a transport measurement I'm showing you, where you see a transition temperature of about 106 Kelvin at about 132 GPa in selenium hydride. Now, what it tells you is that you could do these kind of directed measurements and possibly understand the complexation involved in looking at systems which are more than just binary systems. Okay, in fact, we did cage absorption studies. Again, you can do these at HPCAT. We can do the absorption spectroscopy. And what we do see is an increased p orbital character of selenium that modulates across the superconducting transition. So it's telling us already that, this cage is not only stabilized by the central metal atom, there is a certain amount of modulation of electronic structure across the cage by the central metal atom, telling you that you could, in principle, manipulate that central metal atom in whatever way you want from theoretical calculations and modulate the transition temperature. Okay, now, of course, I want to, I'm getting close to the end. I want to come down to the latest discovery, which is the room temperature superconductivity in carbonaceous sulfur hydride, a brilliant piece of work. And I think it's brilliant from 2 aspects. One is the fact that intuitively you understand from that simulations, which I told you earlier, that replacing sulfur with carbon or doping sulfur with carbon is going to modulate your transition temperature based purely on the fact that if you look at two different binary systems, which is methane hydrogen and sulfur hydrogen, or hydrogen sulfide and hydrogen, you do get a certain amount of systematics. And this work showed that you can actually increase the transition temperature with increasing pressure, albeit, of course, there is a little bit of a gap in our understanding of what actually is the constituent of this system. We know it is carbon, sulfur, hydrogen, and it is hydrogen sulfide dominant system, but we don't really know what the carbon content of that is. There have been more recent papers which have talked about what the structure is, but they're all indirect assumptions or indirect systematics obtained from just the volume points. But I think the bottom line is, lo and behold, the journey started with trying to understand where we are with metallic hydrogen, and it has come to a point where we actually see a room temperature superconductor. Well, yes, it is at pressures of the order of 2.6 megabars, not something which anybody can achieve easily, but it exists. Now, what makes it interesting to me, as far as I'm concerned in terms of looking at it from systematics, is the fact that it is a carbon-based system. And right at the beginning of my talk, I was telling you all to look at your rings with the diamonds in them and understand that nature used carbon. So to me, it looks like there's a complete circle in this, in that we're going back to carbon, something which made diamond, to be able to now talk of transition temperatures close to room temperature in a system which is carbon dominant or carbon-based system. I wouldn't say carbon dominant. And maybe, that's the way we are going to be going if we want to make a room temperature superconductor, which is going to be working for us for whatever things we want to do to benefit mankind. Okay. I wanted to go into a certain epilogue of where it is. There is a paper out in the archive, and which is the work which came out of Maglab collaboration with us. And one of the things I told you right in the beginning, one of the problems really is that you want to do magnetic measurements. And, as all of us who are working in superconductivity know, it's not enough if you do transport measurements. You want to be able to actually measure or show the Meissner effect. And there is a problem in that, because firstly, a diamond cell is a huge chunk of steel. It's a lot of it's going to shield a lot of magnetic field. It's not capable of achieving that high magnetic fields. You want to be able to minimize the heating because of all that metal, and so on and so on. So what we did was, there was a Maglab collaboration, and they designed a Pascal diamond cell which is capable of achieving megabars, and it's a very small cell. I would urge you people to look at this archive paper, which is still under discussion. But this is a Pascal cell which was able to fit to pulse magnets and used at temperatures as low as as low as liquid helium temperatures. The microcircuitry on the anvils was done by FIB. It's a problem. One of the pictures I showed you where we put electrodes on the anvils was by deposition. But when you go to very small anvils and very small samples, you need microcircuitry. That was something which was done. And it's a complex multi-step process of loading samples for this. I would urge people to look at some of the work on yttrium hydride, and which has been done in recent times. It's an amazing piece of work, again, from the Rochester group, where they looked at how they coat yttrium with palladium, which works as not only a hydrogen getter, but also enables hydrogen transport across into the yttrium metal below and to form the hydride. I've not gone into some of the gory details of how we actually synthesize these hydrides and the problems involved in synthesizing these hydrides and the things like that. But anyway, one of the things which they observed in this measurements was the fact that the TC is as high as 294 Kelvin. Okay, you can fit the TC. The field dependence of this TC can be fitted to a Ginsburg-Landau relation. So, things are looking good. I mean, we actually have a material which is superconducting, and it's a fairly high temperature, but already, we're talking of 294 Kelvin. This is lanthanum hydride system, incidentally. But I think the bigger problem or the bigger issue or the big, thing which came out of this measurement, and that is part of the reason why it is sitting on archive. People, have a lot of time. There are a lot of disbelieving people out there, is that we were able to see, or Stan and Audrey, for example, were able to see transition temperatures as high as 550 Kelvin. Now, the question we have is, what is actually driving this? I mean, we started with a simple lanthanum hydride system. In fact, that paper is this paper is that. And now we're beginning to see that there are things which are happening in the system which is driving the transition temperature higher and higher. Just as in the carbon sulfur hydrogen system, where you started with a very low transition temperature of about the order of 30 Kelvin, and you drove it higher and higher with increasing pressure, you are able to drive the transition temperature higher in this system of lanthanum hydrogen by just cycling it with temperature, and it seems to be going up in this thing. Now, I think, of course, we don't have all the details, and all we do know at this point of time is that it certainly is lanthanum hydride based system. What else is in there, we don't know, but it most probably looks like it's not a simple binary system anymore. And that is, of course, borne out by a lot of theoretical calculations which are coming out, and which say that, with ternary systems, for example, there is a theoretical and an experimental paper on yttrium lanthanum system. There is a paper which is talking about the lanthanum borohydride hydrogen system, and so on. But it turns out that you could actually manipulate ternary and quaternary systems based on the same idea of hydrogen content to be able to achieve higher and higher temperatures. I want to stop there. I think I have given a lot of information out there, but I would like to initiate the discussion. If there are questions, I can answer them, and hopefully that will solve a lot of this. I want to acknowledge the people who I worked with. Here are Russ Henley and Dave Mao, with whom I started working in '94 on this. And two of my collaborators are Alex Goncharov and Victor Stushkin here, who were the people who were driving hydrogen, and I was the person, along with Larry Finger, who was driving other compounds other than pure hydrogen to look at under pressure. And it has been a lot of fun working since on those kind of materials and on this things. It's very fulfilling, because I think many people ask, if it's a one day's work. It's not. I mean, it's about 30 years of consistent effort on this field, which has driven this incrementally in terms of capabilities, experimental capabilities, and the understanding of what is going on from whatever little things we can measure both at the lab and in the synchrotron. And of course, it's amazing the number of collaborations I have established over the years, and the number of people I have had the good fortune to work with. And I have put a few of them here, people who were very categorical and very instrumental in my being able to achieve all this work. But I think I want to end my talk by saying that I would like to dedicate this to Professor Neil Ashcroft, who passed away recently. And I think he inspired a whole generation of high-pressure physicists to dream. And I want to end by saying that, I was invited to a Gordon conference on superconductivity in Switzerland when I first came out with this paper on lanthanum hydride. And I realized that, there was a whole hall of people who believed in, should I say, P.W. Anderson, and followed the trail of high TC superconductors. And there were a very small, dedicated bunch of us who broke anvils and went into working on hydride superconductors. And I think I'm proud to say that we came out as winners today. Thank you.
Thank you, Zulu. Any questions from the audience connected through WebEx or hello? YouTube में कुछ messages मिला? मैं आऊँ क्या वहाँ? So this 540 Kelvin was achieved. It's already observed because I have not heard this.
Yeah, this is an archive paper. I mean, unfortunately, I think that's why I put the. That's why I kind of put the. I didn't give too much details about it. It's an archive paper. It's being reviewed, and what was really interesting is the fact that with every cycling in temperature, you increase the transition temperature. And to us, it looks like a case of where the system started as a binary lanthanum hydride and started complicating its constitution by chemical complexity by including with every heating cycle some other element. We don't know what it is, which is driving the transition temperature higher. So in other words, what we think is happening is that as you increase the chemical complexity of the system, you can in principle drive the transition temperature higher. Now, there are a lot of and I don't want to go into details about what actually could be happening there, because the evidence we have is just purely on transport measurements and some diffraction measurements after the sample was finished in the last cycle. But it's all there on the hydride on the archive, and it's a great piece of work, which I think is at this point of time, it looks like discovery science, but maybe that's one way of where it's going to be going. This field is going. I mean, that's the reason I'm saying that when you look at carbon sulfur hydrogen system and you look at the lanthanum hydrogen and X system, you begin to think that theory has to be, theory has to start working towards trying to understand where you can go with ternary or quaternary systems. And of course, experimentally, we are again limited. I mean, there are a lot of arguments out there about whether it is actually superconducting, because it's very difficult to show Meissner effect in these materials. Not because they don't show Meissner effect, but because the measurement itself becomes difficult. I think there has only been one great piece of work on hydrogen sulfide, which came out of ESRF, where they were able to do nuclear forward scattering and show the actual Meissner effect in terms of the fact that the flux expulsion is happening from within the sample. So in other words, what I'm saying is experimentally we are not there yet, but it's a race going on.
So there is a question from Himal Bhatt. He asks, hello sir, is H2O-HN system with high hydrogen content possible at high pressure? What is HN?
I'm assuming hydrogen.
N times H. H2O, H.
Yeah, there is. Yeah. So there is, right? So there is only one system which is known, which is H2O, H2. And that is stable to fairly high pressures. The problem with that system is that you cannot increase the stoichiometry of hydrogen in that. So there is H2O, H2, which is like palladium hydride. I would say it is a similar stoichiometry like palladium hydride. It's a single hydrogen per H2O.
One more point is this whole physics is driven by the back of the mind is the BCS kind of a thing that you are able to predict higher and higher temperatures.
Yes, that's right. So the back of the envelope. Okay, so in other words, BCS theory does not by itself predict any transition temperatures higher than, I don't remember, some 30 Kelvin or whatever it is. That's the highest, I think, the limit you can get from the BCS theory. There's an extension of the BCS theory called the Eliashberg theory, which actually predicts that you can have a London parameter which is higher and higher, and that is what is giving you to higher and higher transition temperatures. But the question then comes back to the fact that, is it BCS? I mean, are we really having, because hydrogen by itself is expected to be a BCS superconductor, right? I mean, there has been a lot of argument about that. I mean, but that's what it is. But are these actually BCS? We don't know. But the fact that the transition temperatures are very close to what is predicted from the Eliashberg theory and the effective calculation of the London parameter in these systems tells you that it's amazingly close to what BCS theory predicts.
Yeah, and there is one more question from Dr. Sanjay Malhotra. It's more about dynamic pressure. Like how does the rate of rise of pressure play a role in, if at all, in this?
How does the sorry, I couldn't get the question.
No, rise of pressure, the rate of rise of pressure,
Okay.
increase. So it's a dynamic pressure in
Yeah.
that sense.
So there is, yeah, I mean, so in other words, yeah, I mean, he's talking about, in principle, what he's asking is, if I understand it right, is it equilibrium or non-equilibrium thermodynamics which is going into this, which is, I mean, I'm not talking about it from hydride superconductors perspective, but in general, yes, it can make a difference. I mean, we are beginning to understand that there are certain transitions which we see in dynamic compression, which we don't see in static compression, or certain transitions which we see in static compression, which we don't correspondingly see in dynamic compression. And yes, yeah, that is true. Yeah, I think Bucci had some questions.
Yeah. Bucci?
We can't hear you. I don't know if you can hear him. No.
No. Tata. No.
Okay. Now okay?
Yeah.
You are able to hear? Yeah.
Yeah.
Yes.
Okay. So after a long time, finally some phonons have come, but you say phonons have not big role in mediating the bringing out the superconductivity, because you are saying you are ruling out non-BCS, right? A BCS theory. But when you say, but I'm from your talk, I'm unable to see what is the clear evidence saying that it is non-BCS type.
We don't. In fact, we think that it is okay. Our feeling is that it is BCS. Okay, and it is our feeling of why we okay. How can, first of all, there have been very few experiments which actually look at the phonons, I mean, in this materials. And in fact, some of the experiments which we are trying right now is to look at spectroscopy, X-ray spectroscopy, because that's the only way we can see if we are seeing any low-laying excitations which can correspond to phonons or electron-phonon couplings, which we can get deduced from these materials. It's very difficult experiments. So far, there is absolutely no idea about it. The only reason why we think it's BCS is firstly because the predictions based on BCS theory seem to bear out with experiments, in terms of which materials will show what superconducting transition temperature. And secondly, I think the more important thing is, if you look at the magnetic field dependence of transition temperature, it seems to follow a Ginzburg-Landau relation, which, giving us a fairly high degree of I would say feeling that it is BCS. But the people who are out there are a bunch of theoretical groups which think that it is non-BCS, and it is based on the fact that they think that the transition temperatures are too high, and that it need not necessarily be phonon mediated, because they can't. So we are talking about phonons which are coming from the highest occupied phonon states to interact with the electrons. And so there is no way they can predict that kind of high London parameters to predict these transition temperatures. I mean, so the possibility is to look at other non-BCS kind of mechanisms with this. There are a number of, I'm not an expert on, many body theory and things like that, so I can't tell.
No, I just want see when we say BCS, non-BCS, there is another chunk of larger materials on this cuprates, YBCAO, etc. There you talk about completely like RBS and such type of different models are there. Are you saying that the high temperature superconductivity observed at the extreme high pressures in certain class of materials, it requires a completely new superconducting theory? Neither BCS nor YBCA type of material, so, oxide materials, but this requires a certain new. Then if that is the case, what is that new which you want to talk about?
I don't know. I mean,
With respect
it
to
is.
the mechanism. With respect to your
Yeah.
mechanism.
I mean, I think there are as far as I know, my literature survey, if it is right, there are 2 or 3 schools of thought. One school of thought by Professor Hirsch from UCSD is talking about hole-based superconductivity. There is another group of people from Russia who are talking about a non-BCS superconductivity, which is mediated by some kind of an impurity state in the band gap. And but the problem is, so in other words, what they're talking about is that you have certain impurity states which are kind of creating localized electronic states near the Fermi surface, which are involved in the superconductivity, and therefore that is why it is non-BCS kind of thing. The problem we are getting into is that to establish whether it is BCS or non-BCS, you need certain measurements, especially, you need measurements of the Meissner effect and, flux expulsion and things like that. And those are very difficult experiments. We are not able to do it. On the other hand, as I said, one possibility is, I mean, if you have seen the literature, in the last few years, there have been some great pieces of work from ESRF, where they've actually measured from using X-ray spectroscopy, the meaning of they have observed low-lying excitations, and which gave them energy scales, right? I mean, in other words, whether it is BCS or non-BCS, you can establish it only by establishing what are the kind of energy scales involved in this superconductivity. And so those kind of measurements have not been performed on this. I don't know. I mean,
My
it's
last
going to be
question. Last question experiment. This is theory. Do you use still to, are your measurements are free from non-hydrosity? Because I don't know what medium which will stay still a liquid thing so that the sample experiences hydrostatic pressure.
Good question. No, we are not in a hydrostatic environment. Certainly not.
Certainly
So
not.
it could be, So it could be purely strain-based material also. I mean, it could be that tells you, that there is a certain difference in mechanism. I mean, who knows? I mean, strain could actually be driving your transition temperatures higher.
Yeah. Nice.
One question from
some other lab has to reproduce your measurement, because to reproduce the same strain, same gradients in things will be difficult. I'm looking for repeating your measurements by another group.
I think in that sense, lanthanum hydride was a success story, because lanthanum hydride within 10 Kelvin, there have been at least 4 labs which have independently reproduced the same material from different, routes of synthesis. And they have arrived at, I mean, 10 Kelvin at 260 Kelvin is not much, but I'm saying that there have been repetitions. So lanthanum hydride that way is a very good success story. In fact, we were very, very happy, because when we published our PRL, there was a race between us and the Mines group on who would get it out first. And both of us hit the archive within 24 hours of each other.
Thank you.
I have one question, 2 more questions on the YouTube. My question is, it is not about superconductivity. You have the CH4, H28, that kind of a compound. So you have hydrogen in CH4, hydrogen in this, the other hydrogen are they equivalent? By what I mean to say is, this instead of H2 8 times, you replace that by D2 and keep CH4. Does your physics change?
No. That is the beauty. The physics doesn't change, but you can actually, it's a good question. You can see the isotope effect of replacing the hydrogens. In fact, it is very interesting what you asked, because just as an aside, one of the experiments we did was, we took deuterated methane and mixed it with hydrogen. And so you can see the CH vibrations in the Raman, right? Just as you can see the HH vibrations. when you do that experiment, you actually start beginning to see an exchange between the molecular hydrogen and the hydrogen which is linked to the methane or the carbon, right? And that is itself intriguing. It's telling you that they're not behaving like independent particles or independent entities, but they're chemically interacting with each other.
Mm-hmm. Okay, but can we have those questions? Yeah. Again, Sudhaman is asking, what more can we understand about the superconducting mechanism from these experiments? Add to our fundamental part of physics, whatever this.
So
this sentence properly formed.
Yeah, I think okay, there are some measurements which we can do currently, and I think that is what X-ray absorption spectroscopy has to be pursued. It's a very difficult experiment, but that is probably our only way of trying to understand where or what is the fundamental physics and chemistry of this system. And that is, it takes some amount of work. I mean, but that is being pursued. I think a lot of groups are pursuing it all over the world. And the other measurement is, of course, the one which I'm talking about, the high magnetic field, pulse magnetic field measurements, which need to establish, for example, they need to establish what is the kind of critical currents or critical fields you're having. There is no measure of that. The third measurement, which I would say, is neutron diffraction. I mean, all our assumptions of where the hydrogen is or what the hydrogen is doing or how it sits within the entity is based on indirect evidence. It's just based on volumes, right? So that's because that's the problem with X-ray diffraction. I think till neutron diffraction comes together, I didn't show a bunch of measurements which we did on hydrogen sulfide using neutron diffraction, but I think there is a lot of information which comes from neutron diffraction which we require. For example, what is the order or disorder of the material? How is it, how is pressure manipulating this order? And those are some of the things we would like to understand, and that need to be performed.
Yeah. And Dr. S.M. Sharma is joining here. What is final status of claims of Diaz and Silvera on pure hydrogen?
Yeah, it's a difficult question. All I would say is their pressures were right. I mean, their pressures at which they claimed metallization are not too far off from the pressures reported by Lubert and Ocelli. But I think the experiment performed by Lubert and Ocelli was far more conclusive than any of the other experiments which have been done so far in reporting metallic hydrogen. And so I think, we know the ballpark pressure at which metallization in pure hydrogen will occur, but we don't know anything more than that. I was told that there is some big deal paper coming out in the next month or two from the Mines group. So maybe that's what is going to tell us more about what is happening in pure hydrogen.
Yeah, and a question from Himal Bhatt with reference to your slide on carbonaceous hydrides. What is the future of carbon-based materials?
Yeah, I mean, carbonaceous hydride, again, remember, carbon there is very small. I mean in terms of stoichiometry, if I understand the paper right, and if I understand some of the more recent papers which have come out on that, the percentage of carbon is very small. So it's not really carbon-based, it's carbon-doped. So, I mean, the question then would be, is there some other doping which we can do which would be far more effective in changing the transition temperatures? Again, it's tough. I mean, ternary systems are very, very tough for doing calculations, so it's difficult.
Okay. Yes. Yeah. Yeah. Sanjay ji. Sanjay Malhotra ji.
Yeah, good evening, Professor Somayazulu. A very nice talk. I would just like to know what happens to, are these materials reciprocal? What happens when we remove the pressure?
So I think at least in lanthanum hydride, we did a very careful X-ray diffraction measurement. And we do know that when you remove pressure, you tend to lose the hydrogen. So, so I think it is certain that pressure stabilizes not only the structural moiety, pressure also is key to establishing the superconductivity in these materials. But we know that there are routes for decompressing and keeping the material intact. That's not been done, unfortunately.
Right.
So I don't, I mean, at this point of time, if somebody comes and says, does this research make superconducting transmission possible? I would say no. I mean,
Yeah,
we're very far from it.
that was the sir, second question I was coming. How to use it for transport currents? As soon as we do, it will need pinning sites and other things like a general theory.
Yeah.
So,
Yeah. So I think it's very far from that. Yeah.
Thank you so much.
Thank you.
Thank you. Thank you, Julu.
Yeah.
Once again.
Thank you, everybody. Thank you. It was a pleasure.
So, bye.